Hello, everyone. Good morning and welcome to the talk. I'm Pramod Satya, and with me is Pratik Joseph Dobre, and we are both software developers at IBM working on Presto. And today we'll be talking about how we enhance the Presto C++ functionality using the sidecar. So let's take a look at the agenda for today's talk. So first, we'll be taking a look at what the sidecar is. And in the rest of this talk, we'll be taking a look at how the sidecar is used to enhance the coordinator functionality in a Presto C++ cluster. So first, we'll start by looking at how it's used for function validation. Then we'll briefly touch upon the work we did to add UDF support in Presto C++. Then we'll look at how the sidecar is used for different things like constant folding expressions, validating session properties and types in C++, and validating the conversion of Presto plan fragments to velox plans. Uh, and finally, we'll take a look at how you can deploy the sidecar in a production environment and the future work that is pending. So let us get started. So let's start with some quick background. So we all know that in Presto, we use the REST API to communicate between different servers. And in Presto C++, the workers, they use the same communication layer as the Java workers. So the request response flow and the HTTP endpoints used for things like adding and executing tasks and reporting the status and so on, they're identical to the Java workers and the C++ workers as well. Also, with this design, we have certain limitations, such as the functions, types, and connectors that are supported in C++ Worker. They're not really known to the coordinator because they're hard-coded in the C++ Worker, uh, and the coordinator doesn't know what is and what isn't supported. So because of this limitation on the coordinator, we are not able to fail fast if we encounter a query that will not be compatible with the underlying native execution engine, which is well off in Presto C++. Also, because of this, we have other issues like show commands, such as show functions and show session. They will return information that is relevant to the Presto Java worker and which may not always apply to the Presto C++ worker. So in order to overcome these issues, we can use Presto's plugin interface. However, the existing plugin interface it didn't really cover all the customization requirements for both the workers and the coordinator. So we introduced a new coordinator plugin interface in Presto SPI in order to allow plugins to provide functionality just for the Presto coordinator. And an implementation of this coordinator plugin for Presto C++ clusters is provided in the native sidecar plugin, which is a plugin that allows us to customize the coordinator functionality for Presto C++ clusters. So the native sidecar plugin, it relies on there being a sidecar process. So sidecar process is essentially just a Presto C++ worker, which implements some additional REST endpoints. So the native sidecar plugin, it can make REST calls to different endpoints on the sidecar in order to infer the capabilities of the C++ worker, such as the functions and session properties that it supports. Uh, and we can also use this sidecar for other things like validating plans and to optimize expressions using the underlying native execution engine, velox. So in order to configure a worker as a sidecar, it's pretty simple. You just need to add this config native sidecar equal to true to your workers config.properties. So you can either choose to have a dedicated sidecar process, or you can just configure one of the workers in your C++ cluster as a sidecar, as we can see in this diagram. So for more details about the sidecar architecture and the SBI changes and all that, you can refer to RFC3. And in the rest of this talk, we'll be looking at the different capabilities of the sidecar that allow us to enhance the coordinator functionality in a Presto C++ cluster. So let us start with functions. So in Presto C++, users can call functions that are not registered in the C++ worker. And currently the default behavior is for such queries to fail on the workers during execution, if the query contains a function or a function signature that is not supported in velox. So using the sidecar, we can sort of resolve this limitation, and we can validate functions on the coordinator with the native function implementations. So this would let us fail fast on the coordinator itself for functions that we know are not supported in Presto C++ or velox. So the way we do this is we first expose the function metadata for all the Presto C++ functions that are registered in velox along the endpoint v1/functions on the sidecar. So on the velox side, we obtain the metadata for the different Presto functions from the function registries in velox. So velox maintains separate function registries and metadata structures for scalar functions, aggregates, and window functions. And we can query each registry in order to obtain the relevant function metadata that would be needed by Presto. So in the native sidecar plugin, we'll retrieve all of the Presto C++ functions by making a HTTP call to this v1/functions endpoint on the sidecar, and we'll integrate all of these C++ functions into the coordinator using the native function namespace manager. So what exactly is the native function namespace manager? So in Presto, all functions, they reside in a function namespace, and we use a function namespace manager to add and retrieve different functions from a given namespace. So function namespace, it's just like a prefix for functions, and it's of the format catalog.schema. So the native function namespace manager, it's just a new function namespace manager that we have introduced for Presto C++ functions. So in order to differentiate between the native and Java functions, we use different function namespaces for both of these. So the Java built-in functions, they are registered under the namespace presto.default. And for the C++ functions, we use the namespace native.default. However, this function namespace, it can be configured using the property presto.default namespace. And you should make sure that when you're setting it, you set it consistently on all of the workers and the coordinator. So with this change, show functions will now display only the functions that are relevant to the C++ worker in a Presto C++ cluster. And this is pretty helpful because we have certain functions in C++ or in Presto that are not supported in Presto C++, like tdigest tag and apply and so on. And these will not show up to the user when they issue or show functions. So another thing it helps us with is if there's like different function signatures between Presto and velox, it lets us choose the right function signature based on the cluster type. And this is the case with functions like array sort. So array sort in both Presto and velox, uh, it has a signature to support sorting of an array using a custom function. But in velox, this is like just a general lambda function. However, in Presto, this custom function is sort of a comparator function. So with this change, we can now use the right function signature for array sort that is supported by velox in a Presto C++ cluster. Okay, so now that we know how function validation is done, let us take a look at UDFs. So UDFs, or user-defined functions, they allow users to create custom functions without, having to rebuild your Presto worker executable. Uh, and the UDF code, it can typically either reside in the same process as the runtime, or it could be in a separate process. So we have two types of UDFs, in-process UDFs and out-of-process UDFs. And we are now implementing support for both of these UDFs in Presto C++. Let's take a look at in-process UDFs first. So in order to support in-process UDFs, we use the DLOpen function, and we're building on it a framework in order to support registering of UDFs in velox dynamically from the shared objects. So with this support for dynamic function loading, or the C++ UDFs can now be used for function analysis, as we saw in the previous slide, or similar to the built-in Presto C++ functions. So I will not go into much detail here, but Soumya from IBM will be talking in more detail about in-process UDFs at 1:30 p.m. later today. So please attend the talk on Unfenced UDF Deep Dive for more details. Let's now look at out-of-process UDFs. So for out-of-process UDF support, we define a new standard REST API for remote functions. And this API will support retrieval of function metadata and function execution within a single API definition. So this API is designed to be dynamic in order to allow users to define new functions at runtime. These out-of-process UDFs, they'll be integrated into the coordinator with a new function namespace manager for REST remote functions. As you can see in the diagram, this REST-based function namespace manager, it will provide methods to list functions, retrieve function metadata, execute functions, to add and drop functions, uh, and so on using the REST API. So we're also working on a new REST-based implementation of this function execution framework for Presto C++ clusters, and this is currently a work in progress. So with the standard REST API, users can customize their function servers by just implementing support for a single REST API, and this can be used by both Presto Java and Presto C++. So right now we are supporting the Presto page format in order to serialize and deserialize data, but in the future we'll also be supporting the arrow format. And for more details about out-of-process UDFs, you can refer to RFC7. Okay, let us now take a look at constant folding. So constant folding is a compiler optimization in order to evaluate constant expressions at compile time. So in Presto, we constant fold expressions during query planning or in order to try and reduce the work that is to be done during query execution. So one example is if you have an unfenced function that is being evaluated over a partition column, you can just use this result to prune the partitions before the query is executed during the planning stage. So in Presto C++, currently the limitation is that constant folding happens on the coordinator using the Presto Java function implementations. And in the Presto C++ cluster, we should have the capability to constant fold expressions using the C++ function implementations. And for constant folding, we should also be able to support UDFs. And currently, this is not possible. So using the sidecar, we can optimize and constant fold Presto expressions during the query planning stage. And in order to do this, we introduce a native expression optimizer in Presto, which is an implementation of the expression optimizer interface in Presto SPI, but this is for Presto C++ clusters. So what the native expression optimizer does is it delegates the expression optimization to the sidecar via the HTTP endpoint v1/expressions. So in Presto, in addition to constant folding, there are some additional expression optimizations that are done for certain special form expressions. And we'll be adding these optimizations to Velox by building on the expression rewrite framework so that the expression optimization is consistent in both Presto C++ and Velox. So this is currently under review, and I won't go into much details. But once we get an optimized Velox expression, what I mean by an optimized expression, Velox expression is an expression that has been, optimized using the special form expression optimization rules that Presto has, and that has been constant folded in a bottom-up manner. So once we have that, we'll convert it back to a Presto row expression in the sidecar. And in order to do this, we're introducing a new Velox to Presto expression converter. And in order to test, these expression optimizations that we're adding in Velox and the Velox to Presto expression conversion, we'll be extending the expression fuzzer that's there in Velox. So this is currently under development. Okay, so now let's take a look at session property validation in Presto C++. So right now, the Presto Java specific session properties, they can be set on Presto C++ clusters and vice versa. But setting these properties, they will not really propagate to the workers, so it really has no effect. And ideally, the Java worker properties, they must not be accessible in a C++ cluster and vice versa. So in order to, make this enhancement, we can use the sidecar. So using the sidecar or the Presto C++ worker session properties, they'll be exposed to the native sidecar plugin along the endpoint v1 slash properties slash session. And on the coordinator side, they'll be integrated using the native worker session property provider. So this native worker session property provider, it's an implementation of the worker session property provider in Presto SPI for Presto C++ clusters. So with this change, users they can only set Presto C++ relevant session properties in C++ clusters and vice versa with the Java clusters. So in order to exclude these, irrelevant session properties that don't apply to the cluster type, we'll need to set this config exclude invalid worker session properties to true. So by default, we still allow setting, invalid session properties in order to support heterogeneous environments, and we control this explicitly using this config. So now I'll pass on to Pratik to talk about types.
Thank you, Pramod. I hope you guys are having a fun time listening to all the functionalities of the sidecar. Let's talk about types more. So the supported list of types in Presto is different to the supported list of types in Velox. For example, Presto supports parameterized varchar, but Velox does not support that. So we are kind of using the sidecar in order to provide that information, provide the type supported in Presto C++ to the coordinator beforehand. So how we are doing that? We actually introduced a new type manager, which is the native type manager. What it does, it just has a list of the supported types in Velox right now, but it's just a static list. But eventually, we want to move on to a more dynamic list where we pull in the custom types registered in Velox and provide them to the coordinator at startup time. So that's what we are doing with types. Moving on, let's talk more about the plan checker functionalities of the sidecar. So before jumping into the plan checker functionalities of the sidecar, let's talk about what a plan checker in Presto means. In Presto, a plan checker is primarily used for validating, analyzing, or asserting properties of query plans. It particularly helps to ensure that the query planner is producing expected and correct logical or physical plans. What exactly does this sidecar plan checker help us to do? We are using the sidecar in a Presto cluster to check if a Presto plan can be successfully translated to a Velox plan. With Velox being the new supported Presto evaluation engine now, there's differences between what's supported in both Velox as well as the Java query engines. The optimizer, while generating the query plans, won't understand the difference between Presto and Velox. So that's why there needs to be a check in place with which we could check whether this plan is runnable, executable on Velox or no. Usually, when you have an incompatible plan, what happens is it fails during runtimes, and it's already late at that time because we have already allocated the resources. We have already sent over the fragments to the workers. So we need a way to know whether a plan is like runnable on Velox beforehand. That's where the native plan checker comes in. So how does the native plan checker work? So there exists a sidecar endpoint, which is v1 slash log slash plan, in which you send over a serialized plan fragment. If the serialized plan fragment gets converted successfully over to a Velox plan fragment, you return back a 200 HTTP response code. If it does not, it returns back a 400 HTTP response code with the failure that happened. Depending on that, you can proceed further. If you want to take a look at the plan checker more, you can refer to RFC 008 for that. Yeah. One of the major use cases of the sidecar plugin or the native plan checker capabilities of the sidecar could be during the migration of Java clusters to C++ clusters. So we actually introduced a new router scheduler plugin to help us do that. So this scheduler plugin is gonna act as a bridge between Java and C++ clusters. So what this plugin actually does is like it uses a statement client to send over each incoming query to a sidecar enabled plan checker cluster. And depending on the response, we route it to a Java router, which is fronting Java clusters, or a native router, which is fronting native clusters. If it's native compatible, we want it to run on native clusters only. What this actually enables us to do is like it enables us to gradually uh, move from Java to C++ clusters in a low risk manner. Additionally, because this is a router chaining kind of setup, you have the first router in which you have the sidecar enabled plan checkers as a plugin. And in the other one, sorry, uh, where should I start from? Just so we got. Additionally, this also gives the users the ability to have full control over the scheduling in the two clusters. Sorry, I think I missed a major point, but let me see how I can uh, add that.
So
Yeah, go ahead.
no, yeah, you can take a look.
Yeah.
We'll be trimming
Okay.
this, right?
Yeah, we'll be trimming this. I'll start from again. So the whole
Cool.
slide again, right? So that's kind
Mm.
of simple for us to trim. Yeah. Moving on to the plan checker router scheduler plugin. So one of the major use cases of the sidecar plugin could be in the migration of Java clusters to C++ clusters. Ideally, during migrations like this, we want to ensure that the query routing happens under the hood without the user knowing about this. For this specific purpose, we are introducing a new Presto router scheduler plugin, which is the Presto plan checker router plugin. Let's step back a little and understand what a Presto router is. The Presto router is a lightweight proxy layer that routes incoming queries to the appropriate cluster based on certain complex routing logic, or it could be simple logic such as catalog, user, or the cluster type. It enables multi-cluster orchestration, load balancing, and isolation of uh, decoupling clients by decoupling clients from direct knowledge of uh, cluster endpoints. This is especially useful in environments with heterogeneous workloads like Java or C++ clusters, ensuring seamless query dispatch. In order to use the plan checker router plugin, you need some kind of router chaining to happen. The plugin acts as an intermediary between two routers, one pointing to a group of native C++ clusters and the other to a group of Java clusters. Simply put, any query submitted via client will route to the first layer of router. The first layer of router is gonna be the router with which you have this router scheduler plugin enabled. It's gonna use a statement client to send over each incoming query to a sidecar enabled plan checker cluster from which you will get a response back whether it's native compatible or native incompatible, and you can make a decision then. This in order for the plan checker cluster to not be bogged down, we actually support a list of plan checker clusters, and they're going to be chosen in a round robin fashion. After you decide which router to route to, it goes to that particular router, and then it's going to choose one of the underlying clusters to actually execute the query. What this helps us to do, it helps us uh, achieve gradual migration from Java to C++ clusters with a low risk, uh, yeah. It also allows us to retain full control over the scheduling logic in the routers pointing to Java and the C++ group of clusters. For more context, you can actually take a look at the link described here. So yeah, let's talk about deployment. So we talked about the sidecar and all its use cases and all its functionalities, but how do you actually integrate a sidecar into a C++ cluster, right? So you could have a dedicated sidecar process to avoid your workers being bogged down. That's one of the ways you could do it, or you could configure one of your existing workers as sidecar as well. Additionally, we actually support all the workers, one or more workers, or all the workers in a particular cluster to be enabled as sidecar, and it should work fine as well. Now, if you want to use the native sidecar plugin, you need a certain set of properties to be defined or configs to be defined. One is going to be you need to have coordinator sidecar enabled too. And all these different functionalities of the sidecar that we just talked about, they're all controlled using individual config files. So for example, if you want to use the C++ function namespace manager or the C++ function registry, you would have to configure the native function namespace manager under etc/function namespace slash native.properties. And if, let's say, for example, you want to use the session properties, you would need to configure it too. If you want to use the plan checker, you need to do the same as well. So the detailed instructions to set up the sidecar will be added soon. Okay, moving on, let's talk about future work. So right now we don't have any support for connectors, but eventually we wanna have support for connectors, as in the connectors that are supported by the native execution engine should be the source of truth. We are kind of working towards that. And also we are kind of integrating, we don't have the sidecar deployment into an Helm chart. If anyone's kind of interested to help with this, then please feel free to reach out via Slack or ping me on LinkedIn. Lastly, I want to say thanks to some of my team members as well as some of the folks from Meta who has helped with the review process for all these functionalities. Thank you. That's it from our end, and we are ready to take any questions, if any.